Hello, this is chapter 4.6, and we're going to talk about the ranks of matrices. And up to this point, we were talking about the vector spaces, and we often define it in terms of the matrix. So we basically use matrices to define vector spaces. But what we didn't look before is that the opposite relationship is also true. We can actually use our vector spaces and some of the terminology and the basic ideas we developed in the previous chapters to learn something new about matrix itself. And one of these ideas is the idea of rank, which is just a dimension of the column space. But we will see later how this dimension of column space will help us to learn more about the matrix itself. But let's just do the example of the rank calculation. It's actually pretty straightforward, so I'm sure you will enjoy doing this. For example, let's take this reasonably massive matrix and let's try to calculate its rank. So this is the dimension of column space. So all we need to do is just figure out how many basis vectors we have in our matrix, and that will give us a rank. And the best ways to start, of course, is write down our matrix in echelon form and calculate how many linearly independent vectors are there. Okay, so let's look at our matrix and see how many pivot columns are here. So the first is a pivot, second is a pivot, and the fourth one. The second and the fifth are actually non-pivot elements, which means that they are linearly dependent. So there is a 3 pivot columns, so there is a 3 linear independent vectors which form our basis. In other words, the dimensions is 3 and the rank of this matrix is 3. So as you can see, it's not really hard to find. So how can it be useful? The rank theorem will tell us some interesting quantitative relationships between the number of rows and columns of matrix and the rank and dimension of the null space. First, the interesting result is the dimensions of column and the row space of a given matrix is always the same, which sounds completely non-intuitive from the first side. So I really strongly recommend you to go to the theorem and look at the proof. It's a truly beautiful proof. So the second interesting result is that there is a quantitative relationship between the rank of matrix and the dimension of null space. So which is equal the number of columns. So basically the dimension of column space, which is rank, plus dimension of null space will always give us a number of columns in the matrix, which is again first sounds really strange and non-intuitive, but it helps to think about this relationship in terms of the pivot columns. For example, rank A, as we see before, is determined by the number of pivot columns. The null space and dimension of the null space determined by the number of non-pivot columns. So of course, the number of pivot and non-pivot columns, which should us a total number of columns. But of course, it's a shortcut, so please go back to the chapter and read the full proof of this theorem. Okay, so I think it's a very although simple, it's very useful results for the future. We found finally the use of this vector space concept and how they can help us to understand matrix more deeply.